Nuclear fusion and its role in saving the world. Contents. Climate change has become an all too familiar problem to mankind. Despite our best efforts, the sheer amount of carbon dioxide that needs to be eliminated from annual emissions is too much in comparison to current efforts to mitigate carbon emissions. Electric cars are great, and renewable energy sources such as solar, wind power, and hydropower are also great. Yet none of them have the strong per unit capacity to replace conventional energy production to an extent that can halt, let alone reverse, our current climate change woes. With the exception of one form of energy production: nuclear energy. Many of us are familiar with the concept of nuclear fission thanks to decades of research and development behind atomic weapons and in a more infrastructural role, nuclear reactors. Before diving into nuclear fusion, it's important to understand the nuances of nuclear energy employed today in current nuclear reactors across the world. The energy produced by boiling water in nuclear reactors, which constitute a majority of the world's reactors, has for the longest time been considered one of the cleanest forms of producing sheer amounts of energy. The average nuclear reactor in the US is determined to produce around 1 gigawatt of power, and according to the Office of Nuclear Energy, a total of 54 nuclear power plants provide 19% of America's electricity, with each power plant's raw power output being comparable to 431 wind turbines, 3 million solar panels, or 100 million LED bulbs. The energy behind these reactors is created when a neutron collides with an atom, splitting said atom and unleashing tremendous amounts of energy through heat and radiation, a process also known as nuclear fission. This cycle of collisions is controlled in reactors to produce a consistent amount of desired heat, which then in turn heats water at the core of the reactor that is pumped into a series of tubes that heats a separate source of water, which generates steam. The steam generated from the tubes in the system turns an electric generator, ultimately producing electricity. All the while, the core water is cycled back to the reactor to get reheated, creating a loop. However, while being efficient in terms of pure energy production, these nuclear reactors still rely on a non-renewable fuel, uranium, and more specifically, uranium-235, which is considered reactor grade, due to how its composition allows for its atoms to be split easier. While uranium in general can be commonly found in many metals, U-235 can only be found in around 0.7% of all natural uranium. Furthermore, the process of nuclear fission in these reactors creates radioactive waste. The US alone generates around 2,000 metric tons of radioactive spent nuclear waste every year. And while this number doesn't mention the nearly 70 million homes it reactor powers and hundreds of millions of metric tons of carbon dioxide emissions that are avoided, the waste is still at the end of the day radioactive waste that has to be stored somewhere. But here comes nuclear fusion. To understand the amount of power that nuclear fusion possesses, it should be referenced that the sun and all stars in the known universe are fundamentally powered by nuclear fusion reactions. Unlike splitting atoms as nuclear fission does, nuclear fusion flings two atoms together, creating one heavier atom and an extra neutron. But because the process yields an atom lighter than the combined weight of the previous two atoms, the excess mass is released in the form of energy. Fusion reactor concepts utilize deuterium and tritium. Deuterium can be extracted from seawater, and tritium is found in an already abundant supply of natural lithium. These two elements are used because of their low melting points and the relationship that allows for a lot of energy to be generated from a fusion reaction. In an ideal reaction with a few grams of deuterium and tritium, a perfectly functional nuclear fusion reactor should be able to produce a terajoule of energy, approximately 4 times as much energy per kilogram of fuel than conventional fission-based reactors. The primary setback in making nuclear fusion the future of energy production is the various constraints that are required to create and sustain the reaction. To make the reaction possible, the reactor has to replicate conditions similar to the sun by maintaining temperatures of over 100 million degrees Celsius, just to allow the deuterium and tritium to fuse. Simply maintaining such high temperatures isn't enough, however, with a consistent amount of regulating pressure and magnetic forces having to also be present to keep the reaction stable enough to produce more energy than the amount of energy required to start the reaction. While the reactions produced in traditional nuclear fission-based reactors are more prone to accidents and catastrophic meltdowns, as seen as recently as the 2011 Fukushima incident, and most infamously the tragedy of Chernobyl in 1986, the extent to which a nuclear fusion reaction can go wrong is severely limited. Quite simply, in the event something goes wrong with a nuclear fusion reaction, the entire reaction would stop due to the complex parameters behind maintaining the reaction in the first place. Radioactive waste produced by nuclear fusion is also predicted to be much less dangerous due to its fuel. Deuterium isn't radioactive, but tritium is indeed radioactive, albeit its half-life is only 12.33 years in comparison to U-235's approximate half-life of 700 million years. The significantly short half-life of tritium, combined with the fact that only a marginal amount of tritium is used in the reaction, makes the concern disposing and maintaining radioactive waste from nuclear fusion reactions a truly sustainable issue. Even though it seems as if a future with nuclear fusion reactors producing near limitless amounts of energy is too far away in time to make a difference in the current battle against climate change, there is hope. As recently as December 5, 2022, a nuclear fusion reaction conducted at the National Ignition Facility in the US was for the first time in the history of nuclear fusion energy able to sustain a reaction just long enough to produce more energy through the reaction than the amount of energy required initially. Even more groundbreaking, as of January 9, 2023, China's experimental fusion reactor is able to sustain continuous reactions for a whopping 17 minutes at 126 million degrees Fahrenheit. The fight against climate change is a fight that must be won for the sake of the future of mankind and the future of the Earth as we know it. Even though we aren't able to fully harness the power of nuclear fusion at the moment, it is imperative that we understand that nuclear fusion provides a gateway to solving our crisis.